record. Oh, I already have one open. I have multiple ones open. Nailed it. All right, so we're gonna create a folder, my first driver. Then we're gonna create a file called mydriver.c. Start with that. All right, and I'm gonna, go ahead.
Just a quick question, like, so for that tutorial that we did for last class, they have the .h file, and we're using like C++.
Yep.
Like, how does H, like, isn't H for like C file?
H is for C, and we're going to be using C in here. Yeah, we're using C in this class.
I just like, thought it was interesting with it.
Yeah, if you're using C++ modernly, it's a .hpp file. Yeah, although historically, the header files were just still .h files when you first transitioned over to C++ from C. The HPP files have some efficiencies for the compiler when you are building for namespaces, a couple other things, but it detects HPP files as the correct kind of file for C++ modernly. All right, so we're going to go through this sample thing, so we have some code we can work with, then we'll make modifications from it. I am going to bounce back to the other one that used that had the big struct, but we're going to start with something simpler to begin with, and then we'll go back and do a read write type thing. Okay, so this site here talks about kernel header stuff. I think we already actually have the headers installed for us in here. I'll go ahead and copy this. So apt-get is a installation package manager for Debian-based Linux distributions. And there's this thing called Linux headers. I'm pretty sure Ubuntu already has these installed, but I will copy this line. I'll go out here to my, Control-Shift-V? Yeah, there we go. So I'm going to go and try to install it. It'll probably tell me it's already installed. You do need to put sudo before this. So it's sudo apt-get install Linux headers dash. Now, actually, let me show you what uname-r gives you. Uname-r gives you the kernel version. Yeah, it was already in here. All right, so and I would assume it's probably in your installs as well. I don't recall having to install that. Most Linux distributions, since they're made for development stuff, has those in there. It's possible if you're running, if you installed like Linux Ubuntu server, it might not have some of the development stuff in there, but make sure you have this. I'll go ahead and actually give you a link to this on Slack. In theory. Big money. Why does Slack run so poorly on here?
It's Clancy's fault.
Is it? That makes sense, I guess. Now that you said it out loud. All right, so I'll paste this into 450. So that's the site we're operating off of here. I just glanced at it before class. It looks like it has a very simple lines of code. So it'll show us how to install a module. That's our focus here. Is last several classes, we looked at makefiles last class. We talked about microkernels and we talked about how Linux has a subsystem for modules that lets you install modules into it to augment, have bolt-on components for a microkernel. So that's effectively what a Linux driver is going to be. So we're, rather than doing a lot of read-write stuff in this one, like we were looking at in the previous code examples, we're just going to get something installed, proving that we are talking. It's going to be the equivalent of a hello world for a driver. Okay. All right, so I'm going to go ahead. I'm just going to copy this code and then we're going to walk through it inside of Visual Studio. All right, and you've seen some of this before in our slides. Let's see. Linux/init.h. Is it just Linux? Let me go to our slides here real quick. Linux init.h. It's not found there. Okay. See if it comes with a different package. Oh, it looks like it'll build it as part of the make file that we'll create. It's just Visual Studio code because this is actually a kernel module. So we just saw that the thing was installed. This is just Visual Studio, I think, complaining about something. We'll burn that bridge when we get to it. All right, so we're including some of the stuff from the Linux kernel itself for modules and also initializing the Linux kernel. This first thing here, this module license actually isn't required. Typically, Linux is an open source operating system. So usually software that you write for Linux will be part of one of the open source licenses, either GPL or MIT, but it's not required. There's probably a default setting that follows whatever the Linux kernel is. All right. Now, if I kind of compare this to the slides, what we had, now have we already looked at some of these, right? Did I walk through these? Like the init and the exit stuff? Or is this the first time you're seeing this? Okay, so I did, but because we looked at the structs too, right? Okay, gotcha. All right, so I think I probably, when we were on this slide, I probably mentioned that the we could think of it like a Java interface for how modules work, where there has to be a way to initialize a module and a way to exit a module. We need to provide functions for both of those things. So you can name those functions whatever you want, but they have to match this particular method header, function header. Okay, so if I go back over here, here is our init function, which this tutorial happens to call hello_init. It's going to take in no parameters, so it's void. And why does it take in no parameters? Because the interface says it has to return an int. It could be called whatever you want because you're going to link it through this module init function. All right, but it has to take no parameters. Okay, similarly, exit returns nothing and also takes in no parameters, but you can name it whatever you want. Okay, so we have our hello init and hello init, which takes in void, so it takes in nothing. This guy, you've seen printf when we wrote our hello world sample C program, right? We saw printf. when you were in the, and you probably also have seen that previously. I've used that example in other classes. And then in the 300 class with C++, we use cout from IOStream, but you also saw printf in there. All right, so here's the new function called print K. What do you think print K stands for? Yeah, printing to the kernel. And if we go to the, out here, if you're ever trying to figure out, you're on Linux and you want to find out what something is, this is the Google before there was Google. We have something called manual pages. So if you do man print K, oh, there is no manual entry for print K. That's pretty funny. See if it lists it under, well, I presume there was going to be one for print K, but there wasn't. But you see here, I still can show you the example. If there's a function you're looking for, you can do man, which stands for manual, and then the name of the function, and it'll give you some information about it. So like the documentation is built in. All right, so similarly, like we looked at malloc last semester. So there's the malloc function. It tells you where it lives in standard lib.h, the different things that are part of that library, so on and so forth. All right, so sometimes the Linux programmer's manual through the man pages will actually give you more direct, easier to read from a programmer's perspective information than going and doing a Google search and having to fish through the results. Just food for thought. All right, so at the end of the day, what are we doing here? We're printing something to the kernel. Now its type is this thing called Kern Alert. And let's see if there's a manual page for that. Presumably, typically things that are in an all uppercase like this are something called macros. So there's going to be a macro called Kern Alert, which is like a constant variable that's going to be equal to something. And we're going to make a pretty good guess here that this is going to be some sort of alert type notification to the kernel. So Kern Alert probably has an int associated with it, some number that is meaningful to the kernel. Maybe it's the number 6 for all we know. But when we write it, we use the all caps Kern Alert, which says, hey, whatever the magical number that the kernel understands as being this type of message, that's what it should be. But more just out of curiosity, let's see if there's a, hello. Oh, no manual page for Kernel Alert either. 0 for 2. Okay, so this is going to be some number associated with that. And then we're writing out hello world \n. Okay, so we're probably writing this as some log file or something like that the kernel's automatically managing. All right, now our init function returns an int. So because we have to have it return an int, so we did that there. So really, when we initialize our module, once it's loaded into the kernel, all it does is print hello world to the kernel, whatever that means. Okay, and we'll see how we can actually talk to it. All right, when we unload the module, so we're going to kind of prove how we can get it into the microkernel and then how we removes it, because drivers are modular, hence the module thing, right? So hello exit, it's again going to print to the kernel, goodbye, cruel world, whatever, blah, blah, blah. All right, now down here at the bottom, so these are our user-defined functions. We wrote those and they had to follow the pattern of return type, parameters, return type, parameters. You can name it whatever you want. And we marry the two together with these two module calls that are found inside of module.h. So if we do a module underscore init, man module underscore init, oh, for the century. I can't believe there's not manual pages for any of these things. I was going to show you the manual page for it, but it makes sense, right? There must be a system call that lives inside of module.h. It's possible in init, but more than likely it's in module.h in this case. We might even be able to see that if I do man module.h. Killing me. All right. So this guy is a function that somebody else wrote that I can say, here is the function that I wrote. that I want you to use to initialize this particular module. Similarly, you're going to let the module subsystem know about what to do when you exit your module, when it gets uninstalled from the microkernel, because we're going to see how we manually install it. We compile it first, so that would be like when you buy a new graphics card from NVIDIA, let's say, and then you go to the website, you download the driver. The compiled version of that driver is effectively the output of what our makefile will do. And then once you download the NVIDIA driver from NVIDIA's website, you install it on your operating system, right? That's what install mod will do, and we'll do that here in a few minutes. Okay, so questions about what this code is doing here. It's the hello world driver code, all right? Pretty straightforward. Okay, so let's go back in here. So we kind of walk through the breakdown thing. All right, so we're going to go ahead and we're going to make a makefile for this guy. And what did we call our file? Did we call it my driver? Good, we did. So I'll go ahead and right-click on my first driver, new file, make file. I'll paste that stuff in there. It uses a couple things that we didn't do last time, but I mentioned that make files have all sorts of special syntaxes and stuff, so we're not going to worry too much about that right now, but we did see what a couple of these things do. So we have make all, and what make all will do is it will call the make function, and if we do a man on make, this one will exist. And actually, I could probably, what was the function call? It was -c. Yeah, -c. So you could walk through and read this, but we're going to get to the section where we see a -c. And we didn't see one. Here's -c, it's the directory where we should be looking for the thing. So if you can't find it inside of a man page, you can do the name of a command, and then usually it's a -h or a --help will give you kind of how do you use this program. So imagine if you're writing this program, so this is kind of, we're seeing like a standard for most Unix-based programs, is they take in a command line argument, and command line arguments that and start with a dash kind of means something to it. So when you do a -h, typically that is, what should I output if it says help? So somewhere inside that program is going to be a wall of text that it prints out in the event that you've asked for help, and it tells you how do you use this program. So this is kind of a standard thing. If you put this almost in front of any program, so if I do ls-h, ls-help, let's go that route. Whenever you see something like that that gives you a big wall of text, I'll say ls-help, and I'll pipe that to more so I can see it one screen at a time. And we see something pretty similar here at the very top. It says usage, ls, followed by options, followed by any sort of file stuff. So it tells us the different things that you can do to ls. So that's a common kind of go-to move whenever you're using Unix-based commands, that they almost always will have a -h or a --help flag that will tell you how to use that command. All right. I've been using Linux for a while. I haven't used it as much in the last couple of years, but it used to be my primary operating system. And just kind of like I said, the same thing with Java is I've been using Java since it was invented, yet I've probably only used, 5% of the language or something like that. So there's a lot of stuff in Linux commands where you'll have to go and say, okay, what is this dude and how does it work? All right, so you'll see us going through some of the debugging type things. Also, Linux is less of a problem for this. as long as you're following, using relatively new code and a relatively new version of Linux, but you will sometimes find some old libraries that just don't work anymore, where you're going to have to, we'll get some weird errors and we'll have to fix them and that kind of stuff. But in any case, so when we do a make all, it's going to make using the lib modules and then the name of our kernel. Remember we printed out a few minutes ago that uname-r thing. It gave us the version of the kernel we have, /build. So this make command is going to use that. I think that is what's going to make this guy work. I think that stuff is embedded in there. So when we do a make, we're going to do it in terms of the Linux kernel libraries that are available to us. We'll see if I have an incorrect assumption there, but I'm pretty sure that's what the case is going to be. All right, so we'll make this with these modules. Make clean, we'll do the same thing. Now this is where it's going to ultimately put my module. These are built modules. Okay, so my output will go in there so that we can then install it. All right, so I'll save this file. See, I'm missing one thing. Yeah, this is what I'm missing. First driver. Okay, this will actually fix the problem I mentioned. So I'm going to copy. So when I copy a file, -r says recursive. So I'm actually copying a directory. Okay. So the directory I'm copying is the directory /user/lib/modules, the name of the kernel /build/include Linux. And you're going to see the connecting piece here in my code. This is Linux/init.h. So I'm copying a directory called Linux that lives in the kernel library. I'm copying it into my local library for building our driver. Okay, and we'll go into that directory here in a second after we do this. All right, so that's what this command does. I'm saying I want to recursively copy a folder. Which folder? The Linux folder found here. Where am I copying it? I'm copying into the current directory. That's what dot says. Okay, so it said no such directory, so we'll find out the actual name because I copied it from there. So let's do user lib modules. Nothing in user lib modules. Nothing in user lib modules. One moment. Ubuntu Linux module folder location. Let's see if they put it in a different place. Lib modules, so /lib modules. What is uname for this guy? Uname.r. So 4.15.135 generic. So I can actually just go back to our original directory. CD, CSC300, CSC450. I'll show you another command here that can be handy. Effectively, the difference thing is the command I copied was looking in user lib, where it actually was in just /lib in Ubuntu. But let's say I don't want to have to go and find that command again. If I type in history and press enter, it shows me the last bunch of commands that I've done. And you can also do you can pipe this to, I can pipe it to grep and say, only do the ones that have uname in it. I think the command I was looking for had uname in it. So that's going to show me these, and you see this was the one I was looking for, 1671. So you can reissue that command by saying exclamation point. So usually you would pronounce that bang 1671. And that tries to run it. We get the same error we had before because that wasn't a directory, but then I can go back and take the user part out of that. We're looking in /lib, /modules, whatever our current kernel version is, /build, /include, /linux to the current directory. Let's see if that guy existed. It did. All right, so I was copying the right folder. I was just trying to copy it from user local lib. Instead of just /lib, or I was trying to copy it from user lib instead of just lib. So now you see I have a folder here called Linux. If I go into this Linux folder, we're going to see that we have I don't have the So this is where that actual folder lives. It's a symbolic link. So this gave me a symbolic link to that guy. I'll see if I can get us in there. No, that's not what I wanted. CD // Linux. Where is the CD /lib /modules /135 generic / going to build / include Linux. Okay, and then in here we should have a init.h. All right, so we have hidden in the system somewhere was a folder called Linux that has all these header files in it, okay, that we're using. These are not things we're going to be changing. They're part of the Linux kernel, but what we needed to do is we needed to copy the symbolic link to that folder, to our local folder, so that when we build our kernel, it can build it in terms of those header files. And this has to do with, if I go back here, sorry, got me to the right place. This has to do with the difference between user address space and kernel address space. Certain things are protected under the kernel and are loaded as part of the kernel. And my way of getting to those things is through what's called a symbolic link. There's symbolic and there's also hard links. Doesn't really matter for us. The point is that when we compile in our user space, we need to have access to the header files that are part of the Linux kernel. And in order to give ourselves access to those things, we had to make sure we had a link to where they are so that when we use our make file to build, it can find the header files to do the magic, okay? Okay, so where am I right now? Okay, so now we're in here. So now we're actually going to use our make file. So when we do an ls, we should see those 3 files there like we saw. So I do an ls, I see my link to Linux, make file, and my driver. If I do an ls-al, notice here it shows that this guy is a link to another place. All right, and that's why it's in red. All right, but I have my files that I need to have here. So now we're going to go ahead and we're going to just type in make. Okay, we can also type in make space all if we wanted to, and both will do the same thing. So I'll type make. Was this the same issue we had last time? Here's my make file. Oh, I think it's that. All right. So same thing that we ran into last time, that I copying and pasting things in, you get some weird results. So it is trying to make this file using our lib directory. So it's entering the Linux headers directory to get at those things I told you about. It is then calling CC, which is the typical Unix C compiler. So CC is actually probably, if I do a echo $CC, I bet you it's GCC on here. Isn't it not $CC? Well, whatever. This is going to be one of our environment variables. It's probably on Linux. It's probably linked to CC or GCC rather, the GNU compiler collection, instead of the historic Unix C compiler called CC. Doesn't matter. It's compiling it. All right. So it compiled here. We got one module out of it. And then this is where it actually does the linking with the kernel. So notice here, our output is actually a kernel output file. Okay, so this did all the magic for us. So now I have some new stuff. All right, I got a bunch of files here. We have our object code output for my driver. Okay, but then we have some module stuff that was built in terms of the module kernel library. We have our kernel output stuff for my driver. I don't know about the symverse thing. I don't remember seeing that before. So maybe that's something newer, or I just am forgetting from the module thing. Okay, but most of this wasn't stuff we wrote, right? Most of this is going to be things that are going to be used by the module subsystem to install a module. Okay, so now, so we did our build. Presumably all that stuff is working. And just as a quick thing, if I do a make clean, notice it takes us right back to where we were. So that's what that clean thing is there for. You can give a directive and say, hey, get rid of all that junk that I just created because I no longer need that, or something like that. Go ahead. -C in the make file. This guy? Yeah, that's the directory that we're telling it to look into. So we're saying we want to make this in terms of the stuff that lives inside of this build directory. That's what gave us access to some of the kernel elements. Yeah, and if we did a, if you remember a few minutes ago, I know I've been bouncing back and forth. If you did a make -H, it shows us what C is. So change to directory before doing anything. So effectively, this makes sure that you're compiling from the context of that directory, as if you're sitting in that directory, because there's stuff in that directory that it's going to need. But that stuff lives in kernel space. Well, that's not really an accurate term I keep using. When I say it lives in kernel space, it's better to say it lives in a protected area that has security rules associated with it. You can't access that directly. You wouldn't be able to build in terms of those things directly. You need to use, you kind of need to, like, this is almost a hack where you're using this compile time flag, this make flag that allows you to, behind the scenes, because make is already a compiled program that allows you to have some limited super user privileges. It allows you to change your context during the runtime of make. Whereas the end user, we don't have a whole lot of things. We can't sit there at the keyboard and type new stuff. But as part of that ninja move of making, we can change our context so that compiling happens in a certain directory. Make some reasonable sense without getting too deep into Linux's workings. It used to be a lot less protected. Well, and so did most operating systems, right? You know, it used to be just kind of go wherever. You could just go to rm-rf/ and just delete your whole file system. No problem. Then you had to do that as super user after that. Now I bet you, even if I try to do that as super user, it's probably gonna say, look, buddy, are you sure this is not something you probably want to be doing? All right, did I already do make here? So I'll do make again. We'll get all our stuff. All right, so now we have all of our stuff. Ultimately, the actual driver is that kernel object file, the .ko file. So we want to, as super user, so sudo means super user do. So as super user, we want to install a module. That's a pre-built command called insmod, install module. What module are we installing? mydriver.ko. Okay, and that's done. So we now, and we had to do that as super user because at that point in time, we are now talking to the microkernel. In fact, we'll go through this part and then we'll uninstall it. And then I'll reinstall it without super user. And we should see an error message saying that you don't have the privileges to plug stuff directly into the kernel. Prove that you are who you say you are type thing. All right, so we installed our module that we compiled right here. All right, now we're gonna, so there's a command, dmessage. So if I do, so printer control the kernel ring buffer. So think of this as like a kind of a global log file, something like that. All right, so dmessage used to examine or control the kernel ring buffer. Default action is to display all messages from the kernel. So as modules are loaded into the kernel, something has occurred, right? So it's going to be in there. So they're asking us to do that and then do a command called tail. You've seen me before use a command called more, right? So you see how they're saying dmessage pipe to tail? If I say dmessage piped to more, this is going to show me the top of that output. And then I would have to press tab a bunch of times until I finally got to the bottom. Here's all the stuff that's happened in the kernel. A lot of stuff, right? But if I do pipe to tail, this shows me what's at the end. Realistically, we could probably just say dmessage, and I'm guessing it'll give me the same thing. Plus, it shows me cool color. That's what the Kern Alert must do. The block red text. Make sense? So there's evidence that our driver indeed got loaded into the kernel. Okay. Now you can also check to see that it's loaded. So there's an ls mod. So just like ls shows you a directory listing of your current directory, ls mod shows you a listing of the loaded modules. So if I do man ls mod, show the status of modules in your Linux kernel. These are modules that either came with the Linux kernel or modules that we've added after the fact. All right, so just like I type in ls here and press enter, ls mod shows me the current modules in the Linux kernel. One of them should be called my driver. So here's my driver.ko. All right, found that guy. All right, we can also, there's a directory called proc modules. So let's make sure that actually exists in here. Here's proc modules. And there's nothing in that directory on here. Doesn't look like there's anything in here. My guess is maybe it's, oh, actually it's a file. It's not a directory. That's why they're doing a cat on it. So cat is, I'll show you, it's concatenate. So if I do man cat, concatenate files and print on the standard output. So if I want to see what's in a file, just really quick dump to the screen rather than having to open it or whatever, I can say cat /proc /modules, and it'll show me the stuff that is in that file. These are all of our loaded modules. If I then want to grep for something, which allows me to kind of search through it with a regular expression, so then I can search for my driver. And there it is in that file. So a bunch of different ways we can prove that our module thing is loaded. Make sense? So far, so good. All right. Lastly, we'll go ahead and remove our module, my driver. So there's been a mistake. We didn't want to install that driver. We want to uninstall it, whatever. So we'll do sudo remove mod. And you can a lot of times tell whether something exists. Like I just typed in RM. If I type in RM and press tab a couple times, it'll show me what possible options I have. And then I see RM mod. So you can start typing most of it and press tab and it'll complete it for you. That's a bash shell thing in Linux. So sudo remove mod my driver. And that should have removed it. And now we can do an ls mod grep my driver lowercase m. We see we got nothing. Make sense? It's been removed. All right, so if we go back, again, if I do history here, we see that our command to install was 1717. So I'm going to do insmod my driver. So we're going to do this not as super user, and I expect it's going to give us some feedback. Okay, error, could not insert module, operation not permitted. We're not allowed to do that unless we're the super user. All right, make sense? All right, and if we go back to dmessage and look at the tail, we should see its exit thing, what happened on its way out as we uninstalled it, and there's our goodbye cruel world. Or if we want to see it in cool looking red, just do dmessage, and then you get the Kern Alert. All right, that makes some sense? All right. So a lot of moving parts there, right? You had to do quite a bit of Unix commands and things like that you probably haven't done before. So what we're going to do, just to kind of limp into making sure you all can do this, as we can start adding to what our, right now we're not even, we didn't even use a module at this point, right? We created a driver that technically, in its most basic sense, is a kernel module. We installed that kernel module. But remember when we talked about at the high level, the things we would do with drivers, and one of them, you remember we had that big struct? One of the things we might want to do is read from a device. Okay, because devices, everything's a file in a POSIX-based operating system. So one of the things we might want to do is read from a device, and that will give us the stuff that that device does. Well, we didn't write read yet. That's kind of our next step, is we're going to now start making our driver do stuff when we call upon it. Okay, but our homework for next class and let me I put it on Slack in a Linux kernel module example. Oh, actually, that's not quite the same one. Oh, I put it up on Slack. So homework, I'll just go back to right here. Let's just go right before this guy. So we'll say homework, follow the tutorial found on Slack that we also followed in class, i.e. watch the video. Get your own version of a kernel module installed, proven that it is installed, removed, and proven that it is removed. Submit a screenshot of each of those steps, indicating that you successfully loaded and unloaded the module. Finally, show a screenshot of the message. Ay, ay, ay. Of the message that shows your hello world, and goodbye messages. Make sense? So this should have you interacting directly with the Linux kernel, loading and unloading a module, and should get you some practice using some of those commands and things like that. It's going to be a little tedious probably at first. You'll make typos and stuff, but you should really feel like you're using your operating system. Questions, comments, concerns, bribes? All right, I will see everybody on Friday.